Hi, this is David Voss, CCIE 11372, and in this video, we're going to cover routing protocol concepts to introduce you to routing protocols for your CCDA exam.
Cisco wants you to be able to identify the attributes of routing protocols so that you can make the correct design decisions. The fundamental question is, which routing protocol should you use? When answering that question, you must keep in mind the following characteristics of routing protocols. And Cisco wants you to remember all of these. First is scalability. How large is your network now? How large will it become? This is important because there are versions of RIP, or actually all versions of RIP, have a maximum hop count of 15 routers. OSPF and EIGRP scale much better, and BGP is the primary routing protocol used on the internet, so obviously it scales very well, and many companies in fact use BGP internally for that reason. Vendor interoperability. Will you be using all Cisco routers on your network, or will it be a blend of Cisco and non-Cisco? Why is that important? Well, RIP and OSPF work fine regardless of vendor, and now even Cisco has taken steps to ensure EIGRP can be used by any networking vendor. The question is, do they support it? RIP and OSPF and BGP most likely, EIGRP maybe or maybe not by non-Cisco vendors. IT staff's familiarity with the protocol. You and the IT staff at your company might be much more familiar with one routing protocol over another. I worked at a company where we had an internal debate over EIGRP versus OSPF. And the tipping point for the conversation was, what protocol do the engineers already know or want to learn better? It was OSPF. And therefore that's what we went with as far as our design decision. That was the tipping point. You will have the same debates internally and should be prepared for this in your decision-making process. Speed of convergence. A benefit of dynamic routing protocols over static routes is the ability for dynamic routing protocols to reroute around network failures. When this failure occurs, the network recalculates and reaches a steady state condition. This is called the state of being a converged network. The amount of time for the failure to occur is called the convergence time. Now, some routing protocols have faster convergence times than others. This is important because when a network is not in a steady state, data can be dropped or looped within the network. You should know that because RIP and BGP might take up to a few minutes to converge. By contrast, OSPF and EIGRP can converge in just a few seconds. The capability to perform summarization. Large enterprise networks can have routing tables with many route entries, and network summarization allows multiple routes to then be summarized into a single route advertisement. So it reduces the number of entries in a router's routing table. That eats up less memory, and also CPU, because it reduces the number of network advertisements that need to be sent. And that can obviously increase convergence time as well. Here's a perfect example. Let's say we're looking at the routing table of a core router, and it knows about all the branch offices. And let's say there are 255 branch offices, and each are allotted a /24, and they're assigned a 192.168 x.0/24 network. Now, sure, the core router has individual entries for all of these routes and knows how to reach all of them through separate interfaces or tunnels. But all these routes do not need to be passed individually throughout the network onto a neighbor through a route advertisement. They can be summarized using one summary route, 192.168.00/16. So as you can see, using summarization, we're saving a lot of memory and CPU by simply summarizing all of these routes into one single route. Interior or exterior routing. A key term you need to understand is AS, which stands for Autonomous System, and this is a network under a single administrative control. A network might be a single AS, and when it connects to, let's say, another network, let's say an internet service provider, then it's connecting to a separate AS. When you're selecting a routing protocol, you need to determine, is it running inside your network, or will you be running it with somebody outside of your network? To answer the question as to what routing protocol you should run, you need to understand if you need an IGP, an interior gateway protocol, or a EGP, an exterior gateway protocol. An IGP exchanges routes between routers in a single AS. common IGPs are EIGRP or OSPF, and then RIP and ISIS are also used, but not as much. Today, the only EGP in use is BGP, but please note that BGP is sometimes also used as an interior gateway protocol as well. There are two types of routing protocols. The first type is distance vector. Distance vector routing protocols send a full copy of the router's routing table to directly attached neighbors. Now, obviously this is not very efficient because it's sending information to a neighbor even if the neighbor already has that information. This can lead to slower convergence time. With slow convergence time, you then can introduce routing loops. The routing protocols that are considered distance vector are RIP and EIGRP. There are two mechanisms that you can use to deal with routing loops that Cisco wants you to know. The first is split horizon. This prevents a route learned on an interface from being advertised back out that same interface. I'll show you a diagram in a minute so this makes more sense. And then there's poison reverse, which causes a route received on one interface to then be advertised out the same interface with an infinite metric so that nobody actually wants to use it. But let's go ahead and take a look at the diagram so we can better understand the issue with routing loops and distance vector routing protocols, and then what we can do about it with split horizon or poison reverse. As you can see here, we have a basic point-to-point network, router 1 connecting to router 2 over serial interface, and then a network 192.168.1.0/24, which is then advertised out serial 0 over to router 1. Router 1 then learns that route and places it in its routing table, as you can see here, with a metric of 1 hop. Now what if Ethernet 0 on router 2 were to go down and the network were no longer available? The problem with distance vector routing is that router 1 is going to send its full routing table over to router 2. Well, router 2 does not know about 192.168.1.0 anymore, so when it receives the subnet advertisement from router 1 of 192.168.1.0, it's going to accept it and place it in its routing table with a metric of 2. And this is where we introduce routing loops. Router 2 will then forward traffic over to router 1. Router 1 thinks it can reach that network via router 2, and traffic will then loop between the two routers. This obviously is not ideal. Now you've already learned about the two solutions to deal with that, and you'll need to know it for your CCNP exam. Split horizon will prevent a route learned on an interface from being advertised back out that same interface, and then poison reverse, which causes a route received on one interface to be advertised out that same interface with an infinite metric. The next type of routing protocol you need to be aware of is the link state routing protocol. Routers send link state advertisements, or LSA, to advertise the networks they know how to reach. So they don't send the full routing table, just the networks they know how to reach, and only when there is a change in the topology. They only exchange full routing information when two routers initially form their adjacency, but from there on out, it's on a need-to-know basis. The routing protocols that are link state routing protocols are OSPF and ISIS. And the final type of routing protocol you need to know is path vector. BGP is path vector, and it includes information not just about the neighbor, but the exact path that packets take to reach a specific destination network. So when you do look at BGP advertisements, you can see exactly over what autonomous systems that traffic is flowing over. So you've learned about the role of routing in an enterprise network and the different layers of enterprise network design. And then you learn the basic characteristics of routing protocols, which is really going to help you as you solidify your foundation and now you move forward in your CCNP studies. I'm sure you're going to do great and continue on with the video series, and good luck to you in your studies.
Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about RIP Design. Specifically, we're going to first learn about RIP version 1 so you can lay a foundation for understanding RIP version 2. Since that is the version most commonly used today, and if you were to design a network using RIP, most likely that would be the version you would choose. So let's begin with RIP version 1. Now, the major drawback of RIP version 1 and why many don't use it today is that it has classful behavior, meaning that it does not send back subnet mask information. Now, if there is no subnet mask information in the updates, then it assumes that any network is staying within its classful boundary, which, as you know, in most networks today, that's rare. As you can see here, each class has a range of IP addresses that it would support. And if it were to remain on classful boundaries, that would mean that you would not be able to provide VLSM or break down these assigned subnets into smaller subnets. So for example, if you were assigned a network in the Class A range, let's say a 10 dot network, you would not be able to break your 10 dot network down into smaller subnets. So later in this video, we will talk about auto-summarization, and that if it summarizes on a classful boundary, specifically with 10 dot networks, you can have routing problems. So often you will find that you will want to turn off auto-summarization in RIP version 2. Another issue with RIP version 1 is that it broadcasts updates. So it uses unnecessary bandwidth, but it also means that routers that are not even running RIP will constantly receive RIP updates even though they won't process them, because routers that run RIP will broadcast them out all interfaces. Modern routing protocols use a multicast approach in order to solve this issue by sending updates only to routers that really need to receive them. RIP version 1 does not allow authentication, so there is no element of security that can be added to the routing protocol to ensure that it is not sending information to devices that should not receive it. When examining RIP version 2, you can see that many of RIP version 1's shortcomings have been addressed. RIP version 2 has a classless behavior, meaning that subnet mask information is sent in updates so VLSM can be achieved. RIP version 2 also supports authentication to ensure that the person you are sending the information to is the person authorized to receive that information. Now, in addition to plain text passwords, the Cisco implementation provides the ability to use MD5 authentication. MD5 is a hashing algorithm that takes a variable length string of text and produces a fixed length 128-bit output. The advantage of hashtag plain text is that the original message cannot be reconstructed even with the knowledge of the hash algorithm. Now, with regards to advertisements, RIP version 2 multicasts routing updates instead of broadcasting them as RIP version 1 does. So this allows for the efficient exchange of routing updates. Another special feature of RIP version 2 is automatic summarization feature, which is applied to prefixes on classful boundaries. This behavior is a double-edged sword because it can induce problems in real-world scenarios. Let's look at the following example. Router 1 connects to the following networks: 10.10.10.0 and 10.10.20.0 and 10.10.30.0. Router 1 connects to router 2 and then on to router 3, which has connectivity to the 10.40.0 and 10.10.50.0 networks. There are also other networks between the routers, such as 172.16.0.0 and 192.168.0.0. Notice the change in classful boundaries that makes RIP automatically summarize the networks behind router 1 and router 3 as 10.0.0.0/8 toward router 2. This can lead to a problem, or it will lead to a problem. Router 2 will receive the same route from both directions. If it receives a packet destined for 10.10.10.0, it can send it in both directions based on the automatically summarized prefixes it received. This problem is called discontiguous subnets, and it's generated by the automatic summarization behavior of the routing protocol that aggregates those subnets. Solutions for this problem involve not using discontiguous subnets in different areas in the network topology or disabling auto summarization. Let's take a look at the RIP version 2 message format. The RIP version 2 message format takes advantage of the unused fields in the RIP version 1 message format by adding subnet masks and other information. Let's go through some of the key attributes of this message. The command field indicates whether the packet is a request or response message. The request message asks that a router send all or part of its routing table. Response messages contain route entries. The router sends the response periodically or as a reply to a request. Version specifies the RIP version used, 2 for RIP version 2 and 1 for RIP version 1. AFI field specifies the address family used. RIP is designed to carry routing information for several different protocols. Each entry has an AFI to indicate the type of address specified. The AFI for IP is 2. Route tag. Route tags provide a method for distinguishing between internal routes, which are learned by RIP, and external routes, which are learned from other routing protocols. You can add this optional attribute during the redistribution of routing protocols. IP address specifies the IP address of the destination. Subnet mask contains the subnet mask for the destination. Now, if this field is 0, no subnet mask has been specified for the entry. Next hop indicates the IP address of the next hop where packets are sent to reach the destination. And metric indicates how many router hops to reach the destination. The metric is always going to be between 1 and 15 for a valid route, since 16 would indicate an unreachable or infinite route. Another aspect about RIP that you need to know is that it relies on a series of timers for its operations, as described here. The update timer, this is where updates are sent, and they're sent every 30 seconds by default. Invalid, the route is invalidated if no update was received before this timer expires. Flush timer determines the time a route gets flushed from the RIP table. And hold down timer. Updates are not accepted for a route that keeps getting a bad metric. And finally, the sleep timer, which can add delay to triggered updates. The hold down and sleep timers are Cisco specific and are used to enhance the RIP functionality. They were not originally specified in the RFCs for RIP. In summary, here are some key points about RIP version 2 that you need to memorize for your CCDA exam. It's a distance vector protocol which uses UDP port 520. It does not scale well since the maximum hop count is 15. Periodic route updates are sent every 30 seconds to a multicast address. 25 routes are allowed per RIP message, or 24 if you're using authentication. And obviously it supports authentication. Subnet mask is included in every route entry. It's a classless protocol. It does support VLSM, and the metric for RIP version 2 is router hop count. Now, all of these points you need to memorize for your CCDA exam. This video has given you a good base foundation for preparations for your CCDA. If you can memorize what you've learned in this video, you should do very well when asked questions about RIP and how and when you would use it in a network design. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about EIGRP Design. We're going to do a high-level EIGRP overview in this video, and then we're going to talk about the EIGRP components. You're going to see this constant theme of these 4 components. So first, there are EIGRP messages that are unique to EIGRP. There's a unique EIGRP algorithm. There are tables that are, again, unique to EIGRP that you need to know about. And then finally, you need to know that EIGRP supports independent modules. So there's multiple support for multiple different network layer protocols. Now, the way we're going to approach this is, again, it's a high-level overview of concepts that are unique to EIGRP. So we all know that EIGRP can support VLSM, for example, but many routing protocols can. So we're not going to dig into VLSM and EIGRP. We're going to talk about things that are unique to EIGRP. Now, if we're to understand EIGRP, we first need to understand IGRP. IGRP came out in 1986. It is an interior gateway protocol that was once very popular. Distance vector routing protocol. And it used 4 key attributes to develop this distance information on how to choose the best path. So it looked at the link, and then it said how much available bandwidth is there, how much delay, how much load, and how much link reliability is there on this link path or on the multiple links to my path. Well, EIGRP is still an interior gateway protocol, and it is still a distance vector protocol, although many times in the past it had been referred to as hybrid, but those days are pretty much gone. Distance vector is what it's classified as, but it has improved convergence in operations. So it uses the dual diffusing update algorithm, and I'll show you about that in a few minutes. And then again, it has multiple unique tables to EIGRP, which assists in the operations and enhances the operations. And then again, it supports multiple network layer protocols. So how does EIGRP actually work? Well, I tell you what, let's go ahead and open up the hood and take a look underneath. EIGRP has 4 basic components, and these should already start looking familiar to you. It has messages. So messages flow to and from neighbors, EIGRP neighbors. There's 5 different types. We'll dig into that in a little bit. EIGRP has the dual algorithm. The dual algorithm takes the information from those messages and then processes best path and possible best path. Then all the information from the messages and the algorithms get put into tables. So these EIGRP tables hold the data from the algorithm and the messages. And then finally, the modules. These protocol-dependent modules support a variety of network layer protocols. So we're not limited. EIGRP is not limited to just IP. So with regards to messages, there are different types of packet formats. There's 5 different types of packet formats. First, there's the hello message. A hello message is basically a query out to anybody who'll listen, asking if anybody's out there. So a router running EIGRP sends hello packets by default, and it will send those packets out and hope for a return reply. And when it gets a return reply, it'll get that update. And that update contains all of the messages or all of the routes that want to be shared via EIGRP. Update messages are messages with a lot of routing information in them. And then there's the acknowledgement message, which surely you know about from other protocols, but it's simply acknowledging that, yes, I've received your message. And that's key to the reliable nature of EIGRP, which we'll talk about in a minute. There's a query message. So if EIGRP loses a route and does not know how to get there anymore, it will query its neighbors saying, do you have any information about this route? Because I'd like to get that information. And then if a router does have information on that route or on that path, it will reply back saying, yes, I do have information, and here it is. So these 5 messages can be broken out into 2 categories, some that are reliable and some that are not reliable. The reliable messages use Reliable Transport Protocol, and this is unique to EIGRP, but RTP basically makes sure that packets get to where they're supposed to go in order. So an unreliable packet is a hello message. that message is not reliable, but the update message from an EIGRP router does use RTP. So it is sequenced and there are acknowledgments. So there is an acknowledgement to that message, but the acknowledgement itself is not reliable. Then there's the query message. Remember, the query is to ask, do you have information about this route? And that uses RTP, and the response to that query, the reply, also uses RTP. So 3 different types of messages use RTP: the update, the query, and the reply. And I think that's critical to know for your exam. Now let's talk about the EIGRP algorithm, which is dual. Now, to understand dual, you need to understand what successor and feasible successor routes are. When you think of successor, just think of success. That's the best path. So if EIGRP loses connectivity to the best path, it will then run the dual algorithm and ask, is there a feasible successor? Is there a second best path? And if the dual algorithm states, yes, there is a feasible successor, a second best path, it will then promote that second best path to the best path. So that becomes the successor. Once it's the successor, it is then installed into the routing table. So for example, it would be installed into the IP routing table. And then the router would begin to use that new path. So this chart gives you an overview a high-level overview of how the dual algorithm runs. But it's important to know these concepts of successor and feasible successor as you move forward with EIGRP and how dual uses that information. Now, EIGRP uses specific tables to help make it run, and one of the tables that EIGRP uses is called a neighbor table. Now, a neighbor table is exactly what you think it is. It's a table that is comprised of a listing of all the EIGRP neighbors. So, for example, we have a hub and spoke design here. We have router A, router B, and router C. And router A and router B are both running EIGRP. Router A sends out a hello packet, and router B responds back as well, and they've established a neighbor relationship, and router A sends out a hello packet. Router C does the same, and they've established their EIGRP neighbor relationship. So once that happens, router A begins to build out its neighbor table by identifying each neighbor by IP address. So, for example, router B is 172.16.1.1, and he gets placed into the neighbor table. And then router C is 192.168.10.2. and he is placed in the router table as well. So router A now has 2 neighbors, and they are both listed in its neighbor table. But there's also other information in the neighbor table as well. And the router A also wants to know what interface are these routers off of. So router B is off of serial 1, router C is off of serial 2. So should I need to forward them traffic, or I know exactly which interface they will be exiting. And then finally, there's other information that is entered into the neighbor table. There's quite a bit actually, but for the sake of this high-level overview, let's just talk about hold time, because this is a key concept. When you program hold time on a router, it's not local. You're not changing the hold time locally. That information is actually forwarded over to your neighbor routers. So here we have router C, who's changed his hold time to 10 seconds. He forwards that over to router A. And here we have router B, and let's say he's going to change his hold time. This information that they're changing from the default, it gets inserted into the neighbor table on router A. And remember, hold time is basically telling the router, if you don't hear from me in this amount of time, consider me down and flush the routes that you receive from me. So it's important to remember hold time is configured on router C and router B, but the actual numeric change occurs on router A in the neighbor table. Now there's definitely other attributes that are in the neighbor table, and we will definitely go over those in future videos. But on a high-level overview of EIGRP, you need to know about the IP, the interface, and the hold time counter. And just remember, hold time defaults is 180 seconds for low bandwidth links and 15 seconds for T1 or higher. So that'll come up again and again, and you'll probably be asked about that as well. But there are other EIGRP tables that you should also be aware of. And a key table to know about is the topology table. Topology table contains all destinations advertised by neighboring routers. This includes, remember, the successor and feasible successor routes, the best path to a destination and the next best path, respectively. So topology table is key for EIGRP to run. Now remember, within topology table, you can see the route tags. So in EIGRP, you can actually perform route tagging. And all you really need to know for now is that you can identify routes by their origination, which allows for custom routing. So you can tag those routes with a manual entry. So that's all you really need to know for now. But getting back to EIGRP tables. Now, here's an example. We have, again, a hub and spoke design, router A, router B, and router C. Now, router A is going to build out, as soon as it enables EIGRP, it's going to build out these EIGRP tables. And one of the tables, again, is going to be this topology table. The topology table is going to contain critical information for EIGRP to run and make the choices upon what the best path is going to be. So in the topology table, it's going to insert routes that it learns from router B and router C. And then it's going to ask, now that I know about this route, which neighbor did I learn it from? And then finally, it's going to say, all right, I know the route, I know the neighbor I learned from, what metric should I assign to it? Which way should I send traffic or forward traffic? So in this example, the route itself, let's say we'll do a 10.1.1.0/24. And let's say we learn this route from both router B and from router C. So this topology table is filled out with 2 entries for the same route. Again, this is not the routing table yet. This is the topology table. And it has a metric, so let's keep it simple. So the metric to router B is 10, and the metric to router C is 20. So for this simple example, let's just say that the router now realizes that the successor route, the best route, is going to be the path through router B. Now, once the dual algorithm has run and it realizes this, it then takes that route or that path and it places the successor route into the routing table, in this case the IP routing table. So now we know the successor is to router B and the feasible successor path is to router C. So as we can see, it's going to choose the path out to router B. Now, what happens if this route information is lost and router A no longer learns about this route from router B or from router C and it gets flushed? Well, router A, what he's going to do is he's going to send a query to router B and to router C asking, do you know about this route? Because I've lost it and I'm hoping you have information on it. And the neighbors will respond back, but specifically, let's say in this case that router C is the only one that knows about it. Router C will respond, yes, I'm aware of it, and it will send the information over, and router A will say thank you very much, and router A will then insert it into the topology table. It will become the successor, and once it's the successor, it will be placed into the routing table. And then router A will then begin using the path through router C to reach that subnet. And last but certainly not least, we have protocol-dependent modules. So EIGRP and the dual algorithm function in a way that protocols can run and use EIGRP independently of one another. So IP builds out its own neighbor and topology tables. IPX and AppleTalk, they all build out their own neighbor and topology tables, and dual can work with any and all of them. So you've learned a lot in this video that will help you with EIGRP design. We've done an overview and we've talked about the individual components of EIGRP, messages, algorithms, tables, and modules. You'll need to know all this information not only to design EIGRP, but obviously to do very well on the CCDA exam. If you study what's in this video and know it well, I'm confident you'll do really well in the EIGRP portion of your CCDA. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video we're covering OSPF Design. We're going to begin with some concepts you need to understand, a baseline I guess you could say, prior to designing OSPF. And then we're going to get a bit more granular in this video and dig into OSPF concepts, such as administrative areas, virtual links, router types, designated routers, neighbor exchange states, link state advertisements, and best path selection. If you're going to design OSPF properly, you need to understand all of these concepts. We will not go into configuration examples that you can learn in the CCNP route exam, but for the CCDA, you will need to understand these concepts. So let's begin. OSPF is one of the most complex routing protocols that can be deployed in modern networks. OSPF is an open standard protocol, that is, it should be able to run on Cisco and non-Cisco equipment. OSPF is a classless routing protocol, and this allows it to support VLSM. Similar to EIGRP, which uses dual, OSPF uses SPF algorithm to select loop-free paths throughout the topology. OSPF is designed to be very scalable because it's a hierarchical routing protocol, using the concept of areas to split the topology into smaller sections. So it is a very popular protocol in today's enterprise networks because it can scale so well. OSPF takes bandwidth into consideration when calculating route metrics. In OSPF, it's considered the cost. A higher bandwidth generates a lower cost, and lower costs are preferred in OSPF. OSPF supports authentication, just as EIGRP does in RIP version 2. OSPF is also very extensible. It's similar to BGP and ISIS, meaning that the protocol can be modified in the future to handle other forms of traffic. OSPF discovers neighbors and exchanges topology information with its neighbors, acting much as EIGRP does in that way. Based on the collected information and the link costs, OSPF calculates the shortest paths to each destination using, as we mentioned before, the SPF algorithm. The formula for calculating the interface cost is reference bandwidth divided by link bandwidth. The default reference bandwidth is 100 megabits per second, but this can be modified, just as the link bandwidth can be modified using the bandwidth command. Please note that the reference bandwidth should be modified in networks that contain a combination of 100 megabits per second and 1 gigabit per second links, because by default, all of these interfaces will be assigned the same OSPF cost. That's obviously a big design consideration and something you certainly could be tested on. Another aspect that adds to the design complexity of OSPF is that it can be configured to behave differently depending on the topology in which you are implementing it. OSPF recognizes different network types, and this will control following actions, such as how updates are sent, how many adjacencies are made with the OSPF speakers, and how the next hop is calculated. OSPF supports the following network types: broadcast, non-broadcast, point-to-point, point-to-multipoint, point-to-multipoint non-broadcast, and loopback. OSPF automatically selects the network type that is the most appropriate for the given technology. So, for example, if you configure OSPF in a broadcast-based Ethernet environment, it will default to the broadcast type. If you configure it on a frame relay interface, it will default to the non-broadcast type. And OSPF configured on a point-to-point serial link will default to the point-to-point network type. The only network types that you need to manually assign would be point to multipoint or point to multipoint non-broadcast. These obviously are most appropriate for the partial mesh, which is hub and spoke environments, and these must be configured manually. So now that you have a high-level understanding of OSPF, let's go ahead and dig into OSPF concepts, all of which you will need to know for your CCDA exam. We're going to go through these one by one to the level of detail you need to know for the CCDA exam, and we're going to begin with administrative areas. An autonomous system is broken out into areas. So areas are a group of routers that share a same area ID. And these different areas, these different groupings have different functions. And they know different types of information. So you have backbone area, standard area, etc., etc. And each of these areas perform different functions. So let's talk in detail about what some of these areas know and maybe what some of these areas do not know, but also how OSPF is designed around these concepts of areas. So remember, we're talking at a higher level here, but as a good rule of thumb, your backbone area in OSPF, if anybody ever refers to area 0, you know they're talking about the backbone area in OSPF. And this is probably the most well-known area because it is required. And all other areas must connect to the backbone area. So if for area to area communication, let's say you have an area 1 communicating to an area 3, both of those areas must connect to the backbone. So let's start here with a standard area. Now, a standard area, you know, what does that really mean? Well, standard areas can be thought of as equal opportunity employers, I guess you could say, because they know about every route in the autonomous system, in the OSPF network. And they share their routes, but they also learn all their routes from other areas through the backbone. And this is just fine. All of this route sharing is just fine if routers are high powered enough to store every route, but also to run these complex SPF calculations. But just know the standard areas contain LSAs of type 1, 2, 3, 4, and 5. Now next, if you think of a stub area, which we'll talk about next, if you think of a network, you have leaf nodes on networks. Well, that's what kind of a stub area is. It's handy if devices are lower powered, routers are lower powered, or simply do not need to know about every route. A stub area is similar to a standard area, but routers in it are not aware of externally sourced routes directly. And in terms of LSAs, that means that type 5 LSAs are not permitted in a stub area. Stub areas use a default route to exit. For traffic to exit a stub area, it uses a default route. Now, next would be a totally stubby area. And let's take this stub area concept one step further. In a total stubby area, in addition to the lack of type 4 and 5 LSAs, type 3 LSAs, which carry information about internal routes, are also prohibited. The concept of an injected default route still applies here, just like a stub area. So all traffic leaving the area does so using the default route. And then finally, let's go over this concept of not so stubby areas. So, this is an interesting, I guess you could say, concoction, because not so stubby areas can connect to non-OSPF networks that are not a part of this autonomous system, and they can receive routes from those non-OSPF networks or networks that are not participating in the autonomous system. And it will receive those routes through redistribution, and then it can turn those type 7 LSAs and kind of, basically it's going to mask them and make them appear as type 5 LSAs, and then begin sharing them onto the network. So there's your ideas of networks and areas, but all areas in an OSPF autonomous system must be, as you know, physically connected to the backbone area, Well, what if you can't do that? What if you can't connect an area to area 0? So let's draw out this concept of a virtual link. Let's imagine we have a company on the East Coast, and in this company we've deployed OSPF already. So we have our backbone area 0, and then we have other areas that have to obviously connect into this backbone area. So let's say we have an area 1 in the Boston area, and then an area 2, let's say in Florida. But let's focus in on area 1. So in the Boston area, we have area 1 in Boston, and we acquire another company in that area. And it's easy enough for us to connect this new company into our Boston resources. So we're going to connect them into our Boston router very simply. The problem is that even though this company that we've acquired, maybe they're already running OSPF, and we convert them to OSPF area 3 to work within our autonomous system, we still need to meet the requirement of OSPF where an area must connect into area 0. So OSPF allows for what is called, as you know, the virtual link. We will create this virtual link between area 3 and area 0. It's passing through area 1, and this allows us to meet that design requirement of OSPF. So route to area 3 and area 0 see this as a direct connection, and things will work just fine thanks to the virtual link. So there are many different OSPF router types that you need to be aware of. There's the area border router, which connects one or more OSPF areas to the backbone area. There's the ASBR, or Autonomous System Boundary Router, which will be located between an OSPF autonomous system and a non-OSPF network. And then you have your backbone router, which is pretty straightforward, a router with at least one interface connected to area 0. And then another easy concept, an internal router, a router with all interfaces in one area. Let's draw this out real quick, to drive it home. So let's draw out our area 0. And in area 0, you know already, is the backbone. So a router within area 0 is a backbone router. And then we connect to another area. Let's say area 1. This is an area border router. Pretty straightforward concept. There's your ABR. And let's say we have another area we're connecting to. There's another ABR. But we are also connecting an ASBR here because we have a non-OSPF network that we're going to be injecting routes from into our OSPF process. So we are injecting routes in through an ASBR, converting type 7 LSAs to type 5, and those are being forwarded on to the network. And then you have, last but not least, internal routers, which have all interfaces in the same area. Pretty straightforward. So in order for two OSPF routers to communicate, they need to go through this process of exchange states. So you need to understand a basic concept of what these are. Here's the following states. There's the init state, where a hello packet has been sent by a router, it's waiting for a reply. Then the establishment state, where there's the discovery of that hello, and then the election of a DR in multi-access networks. The XStart stage, where a master-slave relationship is started between two routers. The router with the higher router ID becomes the master and starts the exchange, and as such is the only router that can increment the sequence number. Then there's the exchange state, where the slave acknowledges the master's packets, and this information in this state is only LSA headers, and it describes the contents of the entire link state database. Then there's loading, where there's a request for more information. In this state, the actual exchange of link state information occurs. And then there's full synchronization, and in this state, routers are fully adjacent with one another. All the router and network LSAs are exchanged, and the router's databases are fully synchronized. Now, a designated router in OSPF is a key concept that you need to know, because on multi-access networks, a designated router will establish adjacencies with all other routers on the multi-access network, learn all of their routes, and then share all of their routes with all the other routers. And then the BDR, the backup designated router, will fill in should the DR fail. And you can set the DR and the BDR manually, and actually you should do it this way. You should set it using the priority command in OSPF. So understanding OSPF priority is key because you can manually set who the DR is and who the BDR is. Now, it's easy to talk about this and look at a PowerPoint, and you may not fully appreciate how important this concept really is. So let's actually draw it out. So on a typical multi-access network, let's say we have 5 routers and you want to establish adjacencies in OSPF to share routes between them. If they did it that way, where they're all neighboring with one another and communicating with one another, you're going to see that all of these adjacencies are going to add up pretty quickly. And that's going to tax the resources on the routers themselves, but it's really unnecessary. We can share this information in a much more efficient manner. So what we're going to do is we elect a DR, and OSPF, again, has this built in within the OSPF design itself, where on multi-access networks you can elect a DR, and then the DR establishes an adjacency with all the other routers on the multi-access network. It learns all of their routes and then shares all of their routes. So now we just have 4 adjacencies required. Now, if the DR fails and those adjacencies fail, the BDR would take over. Now, regarding link state advertisements, what you really need to know, at least just for now in OSPF, is that a link state advertisement is a packet that contains all relevant information regarding a router's links and the state of those links. Now, there are many different types, and I've listed the key types for you here. And we're going to dig into detail in these different types as we get into the labs. But just for now, know that these are informational packets that have information on a router's links and the state of those links. So now that OSPF has gathered all this information, it needs to know what to do with it. It needs to choose the best path. So it puts all the information in a topology table. And then OSPF, the metric for OSPF is cost. So cost is 10 to the power of 8 divided by bandwidth, and lower costs are preferred. So the best way to understand cost is actually for us just to draw this out to see how it works. So let's draw out a 6 router network. And let's say we have router 1, which ultimately wants to communicate with a network off of router 6. And it will have 2 choices, 2 paths it can possibly take. It can go via router 2 or via router 4 to this network. We'll say 192.168.10 network/24. Which is hanging off router 6. Now, router 1 then calculates using OSPF the cost for each and every link in this path. And it's going to do the same for the path from router 2 and 3 to 6. And then what OSPF is going to do is add up the entire cost to get to router 6. So from going via router 4, that path has a total cost of 20. And going via router 2, that path has a total cost of 25. And we know that OSPF uses the lower cost to make its decision on which path to take. So the total cost of 20 wins out, and we will choose router 4. Now that being said, let's say a new network is introduced that has higher bandwidth links. And even though we have more routers or more hops through this network, let's say there are 4 hops. If the cost is low, and for this case we'll say 5, 5, 1, 1, and 1. If the total cost here is just 13, even though there's more hops, OSPF is going to choose this path because it's more efficient. So that's cost basically explained. That's cost in a nutshell. So here's what you've learned. You've received an overview of OSPF, and then we got a bit more granular to the level you'll need to know for the CCDA exam, including administrative areas, virtual links, router types, designated routers, neighbor exchange states, link state advertisements, and best path selection. I'm confident after watching this video, if you know this information well, you're going to do excellent on the OSPF portion of your CCDA exam. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about ISIS design. Specifically, you're going to learn about ISIS operations, areas, addressing, packet types, network types, and metrics. So let's begin. In recent years, the ISIS routing protocol has become increasingly popular, with widespread usage among service providers. It is also a very flexible protocol that's been extended to incorporate leading-edge features such as MPLS traffic engineering. The ISIS routing protocol is a link state protocol as opposed to distance vector protocols such as EIGRP and RIP. ISIS protocol is an intra-domain OSI dynamic routing protocol. ISIS uses a two-level hierarchy, and it's used to support these large routing domains. A large domain may be administratively divided into areas. From a high level, ISIS operates as follows. Routers running ISIS will send hello packets out all ISIS-enabled interfaces to discovered neighbors and establish adjacencies. Routers sharing a common data link will become neighbors if their hello packets contain information that meets the criteria for forming an adjacency. Routers may build a link state packet LSP based on their local interfaces that are configured for ISIS and prefixes learned from other adjacent routers. And a shortest path tree is calculated by each IS, and from this SPT, the routing table is built. Next, let's talk about areas and the routing domain within ISIS. So an ISIS routing domain is similar to BGP autonomous system. A routing domain is a collection of areas under an administration that implements routing policies within the domain. First, let's talk about the backbone. ISIS does not have a backbone area like OSPF Area 0. The ISIS backbone is a contiguous collection of level 2 capable routers, each of which can be in a different area. Now, speaking of areas, within ISIS, an individual router is only one area, and the border between areas on the link that connects the two routers that are in different areas. And the border between areas is on the link that connects two routers that are in different areas. This obviously is in contrast to OSPF. So as you've already heard, ISIS has a two-level hierarchy. Contiguous level 2 capable routers from the backbone. Both level 2 and level 1 routers live in areas. Routers can be level 1, level 2, or both level 1, level 2. Within the Cisco iOS software, the default configuration is both level 1 and level 2 at the same time. This allows ISIS network to run with minimal configuration in more of a plug-and-play fashion. Level 2 capable routers connect all areas within a routing domain. Level 2 routers advertise their own NSAP address to other level 2 routers in the backbone. And all level 1 routers and hosts in an area must have an NSAP with the same area address. A level 2 router may have neighbors in the same or in different areas, but it has a level 2 link state database with all information for inter-area routing. Level 2 routers know about other areas but will not have level 1 information from its own area. A level 1 and level 2 router may have neighbors in any area. It has two link state databases, a level 1 link state database for intra-area routing and a level 2 link state database for inter-area routing. Next, let's talk about NSAP addresses. An NSAP describes an attachment to a particular service at the network layer of a node, similar to the combination of IP destination and IP protocol number in an IP packet. An NSAP address has two major parts, the IDP or initial domain part and the DSP, the domain-specific part. The IDP consists of a 1-byte authority and format identifier, that's the AFI, and a variable length initial domain identifier, the IDI. And the DSP is a string of digits identifying a particular transport implementation of a specified AFI authority. Everything to the left of the system ID can be thought of as the area address of a network node. The big difference between NSAP style addressing and IP style addressing is that in general, there will be a single NSAP address for the entire router. All ISs and ESs in a routing domain must have system IDs of the same length. All routers in an area must have the same area address. All level 2 routers must have a unique system ID domain-wide, and all level 1 routers must have a unique system ID area-wide. All ESs in an area will form an adjacency with a level 1 router on a shared media segment if they share the same area address. If multiple nets are configured on the same router, they must all have the same system ID. Next, let's talk about packet types. There are 4 types of packets. Each type can be level 1 or level 2. First, there is the intermediate system to intermediate system hello packet used by routers to detect neighbors and form adjacencies. Then there's the link state packet. There are 4 types of LSPs: level 1 pseudonode, level 1 non-pseudonode, level 2 pseudonode, and level 2 non-pseudonode. Complete sequence number PDU. CSNPs contain a list of all LSPs in the current database. CNSPs are used to inform other routers of LSPs that may be outdated or missing from their own database. This ensures all routers have the same information and are synchronized. And then finally, partial sequence number PDU. PSNPs are used to request an LSP and acknowledge receipt of an LSP. Next, let's talk about network types. The types of networks that ISIS defines include point-to-point and broadcast networks. Point-to-point networks, such as serial lines, connect a single pair of routers. A router running ISIS will form an adjacency with the neighbor on the other side of a point-to-point interface automatically. The DIS is not elected on this type of link. The basic mechanism defined in the standard is that each side of a point-to-point link declares the other side to be reachable if a hello packet is received from it. Next, there's broadcast networks such as Ethernet, even token ring. These are multi-access and they are able to connect more than 2 devices. All connected routers will receive a packet sent by one router. On broadcast networks, one IS will elect itself the DIS. The DIS is responsible for flooding, and it will create and flood a new pseudonode LSP for each routing level that it is participating in, that is level 1 or level 2, and for each LAN to which it is configured and connected. A router can be the DIS for all connected LANs or a subset of connected LANs, depending on the configured priority, or if no priority is configured, the layer to address. And then finally, NBMA networks such as Frame Relay or ATM or X25 can connect multiple devices but have no broadcast capability. All other routers attached to the network will not receive a packet sent by this router. Special considerations need to be taken in account when configuring ISIS over these types of networks, because ISIS considers these media to be just like any other broadcast media such as Ethernet or token ring. In general, it is better to configure point-to-point networks on WAN interfaces and sub-interfaces. Next, let's talk about ISIS metrics. Cost is the default metric. It is supported by all routers. While some routing protocols calculate the link metric automatically based on bandwidth, such as OSPF, or bandwidth and delay, such as EIGRP, there is no automatic calculation for ISIS. Using old-style metrics, an interface cost is between 1 and 63. All links use the metric of 10 by default. The total cost to a destination is the sum of all costs on an outgoing interface along a particular path from the source to the destination, and least cost paths are preferred. The total path metric was limited to 1023. This small metric value proved insufficient for large networks and provided too little granularity for new features. The Cisco iOS software addresses this issue with the support of a 24-bit metric field, the so-called wide metric. Now metrics can have a maximum value of, as you can see right here. Deploying ISIS on the IP network with wide metrics is recommended to enable finer granularity and to support future applications such as traffic engineering. So you have learned quite a bit about ISIS. You've learned about ISIS areas and router types, the NSAP address, as well as packet types, network types, and metrics. All this information will be needed on your CCDA exam, and I'm confident if you've studied this video well, you're going to do very well on your exam. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video we are going to cover BGP design. The first thing we're going to do is do an overview of BGP, and then we're going to get a little bit more granular and we'll talk about BGP path attributes, BGP AS path, eBGP versus iBGP, public versus private ASNs, BGP updates, and how BGP advertises routes. All this information you will need to know to understand how to properly design BGP and do well on this portion of the CCDA exam. So let's go ahead and begin with an overview of BGP. BGP is an exterior gateway protocol that uses autonomous system numbers. It uses TCP 179 to communicate between neighbors. And it really is a protocol that requires manual configuration for almost everything. It doesn't really do anything unless you tell it to do it, which I really like about the protocol. Now, it uses path attributes, which are key in decision making on choosing best route. So path attributes define information about a path, but also this information can be used to help decide upon the best path. And we will draw that out in a minute here so you can understand that better. Now, regarding BGP path attributes, there are some that you absolutely have to know and memorize. The first is weight. Weight influences a best route for the local router, and obviously it's manually configured. Local preference influences the best route for all routers in an autonomous system, so this is a shared attribute. AS path lists the number of autonomous system numbers in the path, and this can be manipulated. Origin is a value implying if the route is from an IGP or an EGP. And then finally the MED, which can influence the best route for routers in another AS. So you can influence traffic flows into your AS by sending out the MED to other routers. So here you can see we have two routers that are in autonomous system 700. And then upstream, we have another router in autonomous system 140 and autonomous system 87. So here you see there are 4 hops. But as far as BGP is concerned, it's just counting ASs. So it counts 1, 2, 3 ASs. The AS path is 700, 140, and 87. Why is this important to know? Because here's another flow that has 2 routers in AS 700 and then 1 router in AS 87. Now, according to this path, there's just 2 ASs. That would be the preferred path. It's critical to understand that BGP is concerned about AS path and not so much about hop count. AS path is a key attribute to understand. Now, internal versus external BGP. iBGP is something you would run basically interior to your company. It's BGP connectivity within the same autonomous system. In this, routers do not update AS path. Normally they should never have to because you're running the same autonomous system. And in iBGP, things should always be meshed. Routers should always be fully meshed. And there are ways you can get around this, and we'll talk about that in a little bit. Now, eBGP is external connectivity to other ASs. And routers do update the AS path in those cases. So let's say we have an autonomous system, 200, and in our company we're running iBGP full mesh between all routers. And let's say we have connectivity to 2 upstream providers. One is Autonomous System 301 and the other provider is Autonomous System 450. Now, between ourselves and our providers, we are running eBGP because it's 2 different ASs. And internally, we are running iBGP because we are communicating between the same AS. Now, configuration between iBGP and eBGP is quite similar. The main difference is you're choosing to communicate with the same AS or a different AS. Now, let's say we want to communicate to a web server over the internet, and we have a certain amount of hops. Now, let's say one of those paths through AS450 takes us through quite a few more hops, but it takes us through fewer ASs. So let's just say, for example, we go through AS900 and then AS100. So that's 450, 900, and 100. Those are the 3 ASs we traverse in order to reach that route. Now let's say on this flow through Autonomous System 301, we go through fewer hops but more ASs. Now, even though there's fewer hops, because there are more ASs, we're not going to prefer this route. There are 5 ASs in this path. That is not going to be preferred to the other path, which has only 3 ASs. So we're going to choose that path. We'll choose the 3 AS path. Now let's say we're running a web server inside of our company, and we're running iBGP between these 3 routers, and we're connecting to 2 upstream providers using eBGP. And let's say we have users on the internet who are trying to get to this web server. We can manipulate the AS path attribute in BGP to make them prefer one path over the other. And the way we do that, now let's say our autonomous system is 50, we can manipulate the AS path attribute by adding to the AS path on one of our links. So, for example, the users know that they can reach the web server via one AS. Well, we're going to increase that on the top router, and we're going to manipulate it manually and add our AS over and over again to the AS path attribute. And the users, as far as BGP is concerned, that now is a longer path, and therefore the users will prefer the bottom path because it's only one hop, one AS hop. Now, if that router were to fail, users would then prefer the other path. So you see, you can manipulate traffic flows that way. Now, you need to understand the concept of public and private ASNs, and this shouldn't be foreign to you because you understand public and private IP addressing. So autonomous system numbers are chosen from this pool, and you can use them for private use or public use as need be, but you should be aware of that chart. Now regarding BGP updates that we receive from neighbors, you can receive from your provider a default route only, which many people do, or you can receive a full BGP routing table. That is literally every route that's available on the internet. Or you can receive just partial updates, and that is maybe the provider knows about certain routes via a better path than most other providers. You can just receive a partial update from your provider. So you should know that you can receive those three different types of updates. That should be known for your CCNP route exam. Now regarding advertising routes, advertising BGP routes can be done four ways, either through the manual network command, redistribution of BGP into IGP, or propagation of existing BGP routes, or again manually using the aggregate address command. Maybe the best way to explain these is to simply draw it out. Now imagine we have a router with an iBGP connection and an eBGP connection to an upstream provider. So there's our eBGP connection, here's our iBGP connection, and we're autonomous system, let's say 400. So on a router, we can advertise in four different ways. We can manually specify the network we want to advertise by literally typing it in, network 10.10.10.0 or network 198.110, and we can forward that via iBGP and or eBGP. The other way is we can learn routes via BGP and redistribute that route into, let's say, an interior routing protocol. Let's say if we're running OSPF, we can take the routes we learn from our eBGP neighbor and redistribute them. The other way is to simply pass the routes we're learning from our eBGP neighbor via BGP internally to our iBGP neighbor. So that's just forwarding the information on. And finally, we can again manually set an aggregate address on the router, and that's a manual configuration to aggregate some of the routes. And again, that can be advertised out either way. So the rule of synchronization in BGP, you should simply know this, that BGP will not advertise a route unless it knows about that route via an IGP. That's what you really need to know for the exam. Now you can disable this by typing no synchronization on your router, and then it will simply forward routes that are not in the IGP. So here's what you've learned. You've received an overview of BGP, and we dug in a little bit on BGP path attributes, AS path, eBGP and iBGP, public and private ASNs, BGP updates, and then the advertisement of routes. All of this you will need to know for your CCDA exam, and if you master this material, I'm confident you will do very well on this portion of your CCDA exam. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video, we'll be covering IP version 6 routing protocols. So here's what you're going to learn. You're going to learn about IP version 6 routing protocols, an overview of them and how to enable them. To support IP version 6, all of the IPv4 routing protocols had to go through adaptations. Each had to be changed to support longer addresses and prefixes, and the actual messages used to send and receive routing information have changed in some cases as well, using IPv6 headers instead of v4 headers. But in particular, like their IPv4 versions, each version 6 IGP uses v6 multicast addresses. Those are just a few of the changes. But even with those changes, each IP version 6 IGP has many more similarities than differences compared to their respective version 4 cousins. Let's start with RIP. The overall operation of RIP Next Generation closely matches that of RIP version 2. Routers still send periodic full updates with all routes. No neighbor relationships occur. The continuing periodic updates also serve the purpose of confirming that the neighboring router still works. The big difference between RIP version 2 and RIP Next Generation configuration is that RIP Next Generation discards the age-old RIP network command and replaces it with an enable interface subcommand. Finally, RIP Next Generation allows multiple RIP Next Generation processes on a single router. So an iOS requires that each RIP Next Generation process is given a text name that identifies each RIP Next Generation process for that one router. And there's another difference compared to RIP version 2. Let's go ahead and jump into our lab. In our lab, we're going to be working on router 2 and router 4. And we're going to go ahead and log in and enable RIP. Let's take a look at our interfaces on router 2, and we're going to be working with serial 00 and loopback 1. Now the first thing we'll do on router 2 is we're going to go ahead and assign IP version 6 IP addresses. So on interface serial 00, even though it has an IP version 4 address, we obviously can still add an IP version 6 address. And again, we're going to shorten that so it's a lot easier. We're going to use the ability to shorten that address using the double colon. And then the loopback address we'll place in a different subnet. So we're going to use 2012 and 2017. Well, let's go ahead and enable RIP Next Generation on router 2. And before we can do that, we need to enable version 6 routing. See, by default, a router will route version 4, but not version 6. So we do that by typing in IPv6 unicast routing. And then we can enable our routing protocols. So next, we go to each interface we want to enable RIP on. So first we'll go to interface serial 00. We simply type IPv6 RIP, and then we need to give it a process name. The RIP process, and we can run multiple processes on this router. We don't use number, we will use actually a name. And you can name it pretty much anything you want. For simplicity's sake, we'll just say our process name is routing RIP. IPv6 RIP, routing RIP, enable. So we've enabled it on interface serial 00. We will go ahead and do it on loopback 1 as well, inserting it into the same RIP process. Now RIP is still not running on this router until we enable it globally. And we do that via IPv6 router RIP, and then the process name which we have chosen as routing RIP. Now we will verify that it is running on router 2. So IPv6 protocols, there it is, and you see the interfaces as well that are inserted into the RIP process. Now that being said, we're not learning any routes because we are not, we've not established any neighbor, because we haven't learned any routes from any other IPv6 RIP routers. So on router 4, we're going to go ahead and assign IP addresses to the appropriate interfaces. This on serial 01 is the point-to-point. So we will end this IP address with a .2, sharing the same subnet. And then we will insert loopback 1 into RIP ultimately. And we're going to go ahead and assign it 2018. So it's different than router 2. Router 2's IP address was 2017. And then we're going to go ahead and enable RIP on this router. And again, we need to enable unicast routing for version 6. We need to insert the interfaces into the RIP process. And again, we'll use routing RIP as our process ID, and here we've enabled it. And let's do the same on loopback 1. And it's as simple as typing up arrow now. And then finally, we will enable it globally. And now you will see when we do show IPv6 protocols that it's enabled on router 4. And now we can take a look at IPv6 RIP, and this shows what interfaces are participating, the administrative distance, and update intervals. And here's our routing table. So we are learning the route from router 2, which begins in 2017. So that is actively being advertised via RIP. And so we have version 6, that is RIP next generation, up and running between router 2 and router 4. It's rather straightforward. And on router 2, you will see the loopback from router 6 in his routing table as well. So pretty straightforward. Next, let's talk about EIGRP. Cisco originally created EIGRP to advertise routes for IP version 4, IPX, and AppleTalk. This original EIGRP architecture easily allowed for yet another layer 3 protocol, IP version 6, to be added. As a result, Cisco did not have to change EIGRP significantly to support version 6. So there are many similarities that exist between version 4 and version 6 versions of EIGRP. That being said, there are some differences, and I've listed what you really need to know for the CCNP route exam. So let's go ahead and enable EIGRP between router 2 and router 4. So we already have IPv6 up and running. Let's go ahead under interface serial 00, enable EIGRP. IPv6 EIGRP, we're going to use the process ID of 10. And under loopback 1, we will also use the process ID of 10. And then, very simply, we just need to enable EIGRP globally. And we do that via IP version 6, router EIGRP, process ID 10. And again, we have to do a no shut. And if we look now, under IPv6 protocols, we can see EIGRP is running and the interfaces that are participating. Pretty straightforward. But again, there's no communication with any EIGRP neighbors. So let's go ahead, and you'll see here the topology table for router 2, which just shows the local routes. But again, this idea of successor and feasible successor should look familiar to you, as it is in IP version 4. So now on router 4, we are also going to go ahead and enable IP or EIGRP. And again, we're going to use EIGRP process ID 10, enable it under each interface that we would like to participate, and then enable it globally. Once we do that, the neighbor relationship between router 2 and router 4 will come up over this point-to-point link, and we will see our neighbor right here. So again, you can see we have hold time, up time. Looks very familiar to IP version 4. It should look very familiar. So in many ways, we're kind of slaying the beast. Once you get your hands on IPv6, it actually begins to look pretty familiar. Let's look at our topology table, and we will see what we've learned, not only locally, but from our neighbor. And then finally, let's take a look at our EIGRP routes. And there is the loopback from router 2, which we are learning on router 4 via EIGRP. Again, pretty straightforward. Now regarding OSPF, in order to support IP version 6, an IETF working group took the OSPF version 2 standard and made changes to the protocol to support version 6, resulting in the new protocol named OSPF version 3. To migrate to IPv6, routers run OSPF version 2 for v4 support and version 3 for IPv6 support. Finally, let's go ahead and enable OSPF between router 2 and router 4. So on router 2, again, we're using serial 00 and loopback 1. We're going to place loopback 1 in a different area than serial 00 though. So in interface serial 00, we're going to make that area 0. So IPv6 process ID 10, we're going to insert it into area 0. And loopback 1, we're going to insert into area 24. So this is not done like IP version 4, obviously. There's a pretty big difference here. You're enabling it under the interface itself. Now we do need to enable OSPF globally still though. It may not be identical to version 4, but it does need to be enabled globally. So we do that by IPv6 router OSPF, the process ID, and that is it. Now let's go ahead and enable it on router 4 as well. And we're going to do the same. It will be for serial 01 and loopback 1. So again, under both interfaces, we enable OSPF via the IPv6 OSPF process ID. We're going to insert the point-to-point interface in area 0, and the loopback interface will assign to a different area, which is, we'll create area 34. And then we enable OSPF globally. Again, process ID 10. And let's go ahead and take a look at our OSPF routes. And there we have learned via OSPF the loopback from router 2. We can look at our OSPF neighbors. There is router 2 as our neighbor. Again, this should look pretty familiar to version 4. Version 6 OSPF support, it does not look all that different than version 4. And here you see the LSAs. You can see the similarities between OSPF version 2 and version 3. There's quite a few of them. And understanding the concepts of version 4 will certainly help you in understanding how version 6 works. So here's what you've learned. You've had an overview of each of the version 6 routing protocols that you'll need to know for the exam, and then you've seen actually how to enable them in the lab. I wish you the best of luck in your studies. Thank you.